Have you ever wondered how radio signals bounce around the world or what happens to satellites in Earth's orbit? It turns out that both of these things have to do with one of Earth's most mysterious regions, the ionosphere. And today we're going to talk about what this strange atmospheric layer is, how it affects our technology, and why scientists think it could hold the key to future innovations. So let's get started. First, let's start with the basics. What exactly is the ionosphere, and where is it? The ionosphere is a region of Earth's atmosphere that is characterized by the presence of a high concentration of ions and free electrons. It is located in the upper atmosphere, starting at an altitude of around 60 kilometers or 37 miles, and extending all the way up to thousands of kilometers into space. To put this in perspective, the ionosphere begins well above the stratosphere, which is the atmospheric layer that contains the ozone layer, and ends before the region of space known as the exosphere, which is where the atmosphere gradually fades away into the vacuum of space. But unlike the layers closer to the Earth's surface, the ionosphere isn't defined by temperature or altitude. Instead, it's defined by the amount of ionization, or the number of free electrons and ions present. This ionization is caused by the interaction between the atmosphere and charged particles from the sun, which are carried by solar wind or streams of plasma that flow outward from the sun. When these particles reach the Earth's atmosphere, they collide with neutral gas molecules such as nitrogen and oxygen, and strip them of their electrons, creating positive ions and free electrons. These free electrons and ions then remain suspended in the atmosphere for varying amounts of time, forming the ion. So now that we know what the ionosphere is, let's talk about some of its key properties. First, as we mentioned earlier, the degree of ionization in the ionosphere varies depending on factors such as altitude, time of day, and solar activity. The higher the altitude, the higher the degree of ionization. This is because the atmosphere is less dense at higher altitudes, meaning that the gas molecules are farther apart and more vulnerable to being ionized by solar particles. During the day, the Earth's surface reflects sunlight back into the atmosphere, which increases the ionization. Similarly, during periods of high solar activity, such as solar flares and coronal mass ejections, the ionosphere experiences enhanced ionization due to the increased flux of charged particles from the sun. This heightened ionization can disrupt important technologies such as radio communications and GPS navigation systems. Another important property of the ionosphere is its ability to reflect and refract electromagnetic waves, particularly radio waves. When radio waves enter the ion, they interact with the free electrons and ions and are either reflected back to Earth's surface or refracted and redirected in different directions. This property of the ionosphere is what allows for long-distance radio communications and is exploited in techniques like ion sounding used to study the upper atmosphere. The F layer typically has the greatest ability to reflect radio waves due to its high electron density and is the primary layer used for long-distance communications. Alright, now that we've covered some of the basics of the ionosphere, let's talk about how it's structured. As mentioned earlier, the ionosphere is not a uniform layer, and it is often divided into different regions based on altitude and ionization. The lowest layer is called the D layer, and it is located between 60 to 90 kilometers or 37 to 56 miles above the Earth's surface. The D layer is the lowest region of the ionosphere, and it is characterized by a relatively low density of ions and electrons. The D layer is formed by the ionization of the lower atmosphere by solar radiation, and it is primarily composed of ions of molecules such as oxygen and nitrogen. The next layer is the E layer, which is located above the D layer at an altitude of around 90 to 150 kilometers, or 56 to 93 miles. The E layer is characterized by a higher concentration of free electrons, and it is the main layer responsible for reflecting radio waves. The E layer is also more permanent than the lower layers of the ionosphere, and it is present during both the day and night. Above the E layer is the F layer, which is the highest and most complex region of the ionosphere. The F layer is further subdivided into two sublayers, the F1 layer and the F2 layer. The F1 layer is located at an altitude of around 150 to 300 kilometers, or 93 to 186 miles, and it is more prominent during the daytime. The F2 layer is located at an altitude of around 200 to 500 kilometers, or 124 to 311 miles, and it is more prominent at night. The F layer is the region of the ionosphere with the highest concentration of ions and electrons, and it is responsible for the majority of long-distance radio communications. Now that we know how the ionosphere is structured, let's talk about some of the ways that it affects our lives. As we mentioned earlier, the ionosphere is constantly bombarded by charged particles from the sun, and this can cause significant disruptions to important technologies such as radio communications and GPS navigation systems. For example, during periods of high solar activity, the increased ionization in the ionosphere can lead to widespread blackouts in radio communications. This can be problematic for applications such as aviation, maritime shipping, and military operations, which rely heavily on radio communications. Similarly, The ionosphere can affect GPS signals, leading to inaccuracies in positioning and timing. This can be problematic for applications such as precision agriculture, asset tracking, and autonomous vehicles, which require accurate GPS signals. These disruptions highlight the importance of understanding and monitoring the ionosphere to ensure the reliable operation of critical technologies. But the ionosphere doesn't just affect our technology. It also plays a crucial role in our understanding of the Earth's atmosphere and its interactions with the Sun. For example, the ionosphere is a key component of the Earth's upper atmosphere, and its structure and behavior provide valuable insights into the composition and dynamics of the atmosphere. By studying the ionosphere, scientists can learn more about the distribution of gases in the upper atmosphere and how they interact with solar radiation. Additionally, the ionosphere is a dynamic and ever-changing region, and monitoring its behavior helps scientists track changes in the Earth's atmosphere over time. This can help scientists better understand long-term trends, such as the depletion of the ozone layer and the impact of climate change on the atmosphere. One way that scientists monitor the ionosphere is through a network of ground-based ionosondes, are specialized instruments that use radio waves to probe the ionosphere and measure its properties such as electron density and critical frequency. By analyzing the signals returned from the ionosphere, scientists can create maps of the ionospheric conditions and track changes over time. So now that we've talked about the ionosphere's effects on our lives and how we monitor it, let us shift our attention to some of the exciting possibilities that this mysterious region of space offers for future innovations. One promising area of research is the use of the ionosphere for satellite-based communications. The ionosphere's ability to reflect and refract radio waves makes it an ideal medium for transmitting signals between satellites and ground stations. This could enable new applications such as high-speed internet access from low Earth orbiting satellites and improved communications for remote areas of the globe. Another exciting development is the use of the ionosphere for space weather forecasting. By monitoring changes in the ionosphere, scientists can track the arrival of solar storms and other disturbances in the Earth's magnetic field. This information can help protect critical infrastructure such as power grids and telecommunications networks from the damaging effects of space weather. And finally, the ionosphere holds immense potential for scientific research and exploration. The unique conditions in the ionosphere make it an ideal environment for testing new technologies and conducting experiments in space. For example, the European Space Agency's Swarm constellation of satellites has used the ionosphere to study the Earth's magnetic field and its interactions with the solar wind. By continuing to explore and understand the scientists may uncover new insights about the Earth's atmosphere, the Sun, and the fundamental laws of physics. Alright, so now you know all about the ionosphere. But don't worry, if you feel like there's still a lot to take in, we covered a lot of ground in this video, but it's a big topic. And the ionosphere is one of those topics that seems really complicated. But once you break it down, it's actually pretty easy to understand. We hope we were able to show you that there is no need to be intimidated by the complexities of science. With a little bit of effort and a willingness to learn, anyone can grasp even the most challenging concepts. And who knows, maybe you'll even discover a passion for science that you didn't know you had. Thanks for joining us on this journey through the ionosphere. If you enjoyed this video, don't forget to give us a thumbs up and subscribe for more videos like this. And if you're still curious about the ionosphere, check out some of our other videos on this topic. Until next time, keep looking up.